The next independent variable we're going to test is the frequency of the current that we're driving through the outer solenoid. So I'm going to select on the function generator one of the lower frequency ranges, the 50 hertz range, and the frequency knob is turned down. So I'm going to start with a frequency around 10 hertz, and we'll see what that does to the induced EMF across the smaller solenoid, while keeping the smaller solenoid completely inserted into the larger solenoid so that they're flush. So let's try to get a signal here. I decreased the frequency a lot, so the sine wave has been spread out a lot, so I want to zoom out from the horizontal axis. So I'm going to use this horizontal time per division knob. That's analogous to the volts per division. This is for the vertical axis, and this would be for the horizontal axis, which is time. So I'll keep turning it until we see a few periods. And there is a induced EMF, but it's hard to see, so let me turn up, zoom in vertically on channel 2. Looks like it's triggering on channel 2. It's still jumping around. So that's a trigger problem. Trigger level is at 0. Source, let's make the source channel 1 because it's a little cleaner. That seems to help. Okay. So this says 10 hertz. The oscilloscope says the frequency is 8.8. So maybe we could increase it a little to try to get it closer to 10 using the fine frequency adjustment knob on the function generator. Of course, if you're plotting it, it's probably not critical that it's exactly 10, as long as you have a precise number for the frequency to find where on the x-axis it goes. Okay, let me turn the trigger menu off. Okay, we'll start at 10.1 hertz. So first I will ignore channel 2 and remeasure the current through the outer solenoid to have a baseline current. So let's turn on the cursors, and shouldn't have changed. I didn't change the output level of the function generator. Let's make sure for this part. Doesn't look super stable, but I think we can be confident it's pretty close to 38.5 milliamps. Okay, so 38.5 milliamps and 10.1 hertz. The EMF induced in the small solenoid is, change the cursor to get the peaks here. And that's peak to peak voltage is going to be 83.3 millivolts. And I'll increase the frequency. I'll double it. we're going to explore a wide range of frequencies, so I probably use sort of a logarithmic scale and double things instead of go up a set, add a set amount every time. Decrease the volts per division on channel 2. Now we're at 50 millivolts per division, still at 10 millivolts per division for channel 1. And we want to look at channel 1 and just make sure it's not changing. That's why I'm going to keep it on the screen. So, because if it's changing, that's showing that there's a different current running through the outer solenoid, and that'll mean there's a different magnetic field, like sort of B max through the smaller solenoid. So we're not going to change the peak magnetic flux, we just want to change sort of the rate of change of the flux. Okay, so channel 1 hasn't changed. Channel 2 has. Let's measure what the induced EMF in the smaller solenoid is at 20 hertz, 20.0. And the reading, the cursor measurement says 152 millivolts. So let's increase again to, say, 50 hertz. I guess if we're going with our doubling scheme, then that'd be 40. Let's try that. So 40.0 hertz. The induced EMF is, adjust the cursors, drum roll please, 276 millivolts. And I think if we try to double the frequency again, we're going to run out of room on this range. So I'll turn the frequency knob all the way up, and we only get to 55 hertz. So I'm going to turn it back down, and then change the range to the 500 hertz setting. And that starts us where we left off, around 45. So we can increase to 80 hertz. Okay, there's 80.0, 79.9. Let's adjust our picture, zoom in horizontally. Whoops, that's the wrong way. To just show a few waveforms again. And then we'll have to zoom out vertically on the y-axis. The y-axis only of channel 2. Channel 1 is still the same, 10 millivolts per division. Now we're showing 100 millivolts per division on channel 2. And I will adjust the cursors on channel 2 to show that at 80 hertz we have 545 millivolts measured on across the small solenoid. And we can do the same thing of maybe doubling the frequency. $160.0. Have to zoom out again, channel 2. And the cursors are lined up nicely already. Happy accident. We have 1.06 volts induced on the small solenoid at 160.1 hertz. Increase the frequency again. $320, some odd numbers. So I started with 10 and I'm doubling it. Should have started with 16 something natural. But that's okay. Not going to affect the data. Just housekeeping matter. Okay, zoom out again vertically and adjust the cursors. select the other cursor and bring it up. And at 320 hertz, we have 2.06 volts on the center solenoid. Turn the lights back on. Okay, 300 hertz. Let's go up to, see how high we'll go on this range. Be about 500. So just get another data point on this range. 500, 499.9 hertz. The EMF is 2.90 volts. Okay, let's try one more range. I'm going to reduce the frequency knob, press 5K, the 5 kilohertz range. Then we start at 500. So what happens if we go up to, say, 1,000 hertz? Go up to 1,000. Now you can see, let me turn off channel 2, so let's just look at channel 1 for a moment. As I go from 500 to 1,000, not only is the period decreasing, as we'd expect, but the amplitude is also decreasing. So now we're changing the peak magnetic field inside. So that's an additional variable we don't want to introduce, or at least not take account of. So I will adjust to around 1,000 hertz and then remeasure the current through the outer solenoid. So I'm going to turn on, the cursor's already on, cursor. So the peak to peak current now is only 27.3 millivolts. And that's because the inductance of the outer solenoid depends on the frequency. So it's resisting, impeding the voltage more at a higher frequency. So we're getting less current. So that's something we'll have to keep track of. So at 1 kilohertz, we have 27.1 milliamps through the outer solenoid, and the induced EMF across the smaller solenoid is, turn channel 2 back on, zoom out vertically, and we could zoom in horizontally to get our nice waveform back. I'll adjust the cursors for channel 2, and the EMF is 4.95 volts, so even with a slightly reduced peak flux, magnetic flux through the small solenoid, still has a larger EMF induced. Let's go to 2,000 hertz. So now, as both waveforms are changing amplitude, we'll have to measure both amplitudes. Right, that's 1.99 kilohertz. I'll measure the channel 2, the induced EMF on the smaller solenoid first, 6.46 volts, and then I'll change the cursor to channel 1. There's got to be an easier way to do that. And the peak to peak current on channel 1 is only 17.3 milliamps. Now I'll turn up the frequency once again to 4,000 hertz. I'll zoom in on channel 1. Okay, 4.01 kilohertz. And move the cursors for channel 1, and we see we have 8.75 milliamps running through the outer solenoid, and click channel 2. Cursor. Better zoom out so I can actually see the peaks. .16 volts across the smaller solenoid. See how high we can go on this range, probably 5,000. Something like that. So 5.0, 4.99 kilohertz. .23 volts, and measuring, go back to channel 1 to measure the current, and zoom in on the current. Cursor. .86 milliamps. As we keep going up, this is the higher scale, 50 kilohertz range. See the same pattern continuing. So from 5 to 10 kilohertz. We see once again a increase. Smaller current passing through the larger solenoid, only 3.23 milliamps. And once again, a larger induced EMF. .66 volts at 10 kilohertz. See if I can see 50 kilohertz. Zoom in horizontally. Doesn't look very good. .40 kilohertz. Trigger. Oops, that's channel 2. I'm going to adjust channel 1. Probably now channel 2 is the more stable channel, so I'll change the trigger over to channel 2. Good. And then zoom back out so I can see a few periods. And now we have a tiny current running through the outer solenoid at 40.4 kilohertz. Adjust it, get 40.0. Doesn't, just to be nitpicky. Oops. So for the induced EMF, cursor measured at 40 kilohertz, we see 12.2 volts. I don't think we can measure much more than that on this oscilloscope. And on channel 1, we can't zoom in any more than 1 millivolt per division. And this doesn't look like a very good measurement. Something like 583 microamps through the outer solenoid. We could turn up the output level. I think that's also a good place to stop. So that's induced EMF versus frequency of current run through the outer solenoid.